Okay, so welcome back. All right. So last time we had gone over at least the mechanical aspects of computing partial derivatives. So if I have some function f of xy, partial derivative of f with respect to x and y. These are both functions of x and y in general, in their own right. A way of shorthand writing this was using this notation f sub x and f sub y. This is a notation that's used in a lot of classes going forward just because it's a lot quicker to write. This is kind of the, this is like when instead of writing ddx, you write just a prime. Instead, of course, we can't do that anymore. We have to refer to the variable that you're taking the partial derivative with respect to, since there's multiple of these now. And these would be called the first order partials. Okay. So when you hear first order partials, it means the first derivatives with respect to those variables. Okay, so there are two first order partials. All right. So what about as we computed last time, the second order partials? So writing in this old notation, you might see them written like this. So d2f dx or del x squared. So this is f sub xx of xy, and of course the mixed partials look like this. So I'm not going to keep doing this, but just this is, if you're reading any examples and you see this notation instead. So I guess we were calling this f sub y x, I guess. I think the textbook reverses it. Again, as we saw, it's not a big deal because it turns out that for very nice functions, these mixed partials are equal. The only thing that matters is how many of each variable shows up. So remember, for nice f, f sub xy is equal to f sub yx, and of course this is true. I didn't have to just do it for the second order partials. This was true similarly for any number of x and y partial derivatives that you want. So long as f is nice enough. Now, what exactly does nice mean? It means that for our purposes, you would have to specifically construct an f that fails this condition. The textbook does this in that section, so if you're interested, you can have a look at that. Actually, maybe I'll just look that up real quick. Let me remind myself of an easy example of this failing. Where is it? Oh, now I'm having, let's see here. Oh, yeah, so here's one that fails. Right, this one fails. So if you want to see a function that fails this, define the piecewise function that is, it's x cubed y minus xy cubed over x squared plus y squared. And that is true everywhere except at the origin for xy not equal to the origin. Okay, and it's equal to 0 at the origin. Okay. So it turns out that in this case, if you try to compute the x and y partials at the origin, you'll find that the xy partial at 0, 0 is not equal to the yx partial at 0, 0. Okay, but you see, you have to try pretty hard to construct an example like this. You don't have to worry about that too much. Just know that Technically, this statement that the mixed partials are equal has a caveat, but luckily for us, that caveat's going to be met for every function we encounter, so you don't have to worry about it. Just know that, in general, that statement is not entirely true. Okay. So, what I wanted to talk about is this idea of, like, what is it that we're doing when we compute these partial derivatives? So now we understand how to mechanically do them, right? We just treat the other variables we're not differentiating with respect to as constants, and then we take the derivative like we would in Calc 1 or Calc 2. But what do these mean, right? In Calc 1 or Calc 2, taking the derivative found an instantaneous rate of change, right? So as I mentioned before, think about what the graph of an f of xy looks like, right? So graph of some function of two variables might look like this. Okay, and so at a point like here, right, so let's say down below, here's my domain, right? And so I have some point here down below. And the point is, at this point on the graph, right, say I want to know a similar quantity that I was computing when I found the derivative in the Calc 1 sense for a function of a single variable, right? And as I mentioned before, in Calc 1, when I draw a function f and I talk about the instantaneous rate of change at this point, that is given by the slope of the tangent line at that point, which I compute with the derivative, okay? And when I say instantaneous rate of change, I'm assuming a direction in there, okay? And the reason that I'm assuming a direction is because there's only one direction I can pick, right? There's really only one direction along this curve because it's one-dimensional, right? So I'm either going that way or I'm going the opposite direction, okay? But that's still one line worth of direction, all right? And so at this point, however, there's no direction indicated, right? So if I wanted to talk about the rate of change of this function, well, you can imagine this thing being very bumpy, right? So this thing could be very bumpy, and maybe the rate of change is not really equal in all directions, right? So, we could pick some, let's see, do I have a nice 3D object here that's maybe not too bad? Let me look around here. Well, I don't have, okay, let's see here. Okay, so we have Godzilla spines, right? So if I'm looking, right, and this back is some surface, right, then in this direction along Godzilla spine, there's relatively less change because it's pretty flat right here. So if I'm at this point on the spine and I'm going in this direction, I'm basically not changing at all. It's pretty flat. Okay. But if I were to go off the sides, that is a steep fall off, right? So in those directions, the rate of change, if this is the graph of a function, the rate of change would be pretty steep, right? And so the idea here is that I have to specify a direction, okay? That direction is going to be specified by some unit vector. And once I do that, then I can talk about a quantity that is the instantaneous rate of change in that direction. So this is the notion of what's called the directional derivative, and it is the thing that is going to play the role of the same role that the first derivative played in Calc 1 and Calc 2. So this is the notion of directional derivative. Okay. So what is the idea of a directional derivative? The idea in a directional derivative is that I specify a unit vector. Okay, now the unit vector that I specify is going to just have two components for a function of two variables. So technically it's down here in the xy plane, but I'm going to view it up here, right? And so the idea is that I specify some direction u. Of course, here it looks like I've specified the same direction that's in the direction of the y-axis, but I could specify any unit vector u. What does the directional derivative compute? This is the instantaneous rate of change of the function f of xy at the point x naught y naught. So here's my x naught y naught. And so this point is f of x naught y naught. Right, in the direction specified by the unit vector u. Okay, so this is the thing that I want to compute. All right. Now the textbook goes ahead and defines this immediately, but before I do that, I'm going to define something else that lets me define this a lot easier. Okay. And so, since you see these magic words here, instantaneous rate of change, you see that this is the thing that is playing the role of my derivative from Calc 1 and Calc 2. Okay, so this is finally the object that is, closest to what we're used to from Calc 1 and Calc 2. Okay, so in order to define this, I need to define another quantity first. You'll see in the discussion, or in the description of this video, it's mentioned, and this is the gradient vector. Okay, so I think I have room. So definition of the gradient vector. Okay, so if f of xy is a function with first order partials at x naught y naught. What do we mean when we say that it has first order partials? It means they exist and they're continuous. Okay, so this is at least first order differentiable, right? Maybe it doesn't have its second order partials, but it's got its first order partials. So if f is a function with first order partials at x naught y naught, then the gradient vector of f at x naught y naught is the following. This is nabla f x naught y naught. This is defined to be the vector where in the x slot I have the x partial at x naught y naught, and in the y slot I have the y partial of f at x naught y naught. Okay. All right, so written another way, not in IJ notation, the gradient of f at x naught y naught is the x partial evaluated at that point in the first slot and the y partial evaluated at that point in the second slot. Okay. Now, of course, there's nothing preventing me from defining this for a function of 3 variables. So if I have a function f and it's a function of 3 variables, then just as well, the gradient of f at x naught, y naught, z naught is the x partial of f at x naught, y naught, z naught in the first slot, the y partial of f in the second slot, and the z partial of f in the third slot. Okay, let's do a quick example. So let's say let f of xy be x cubed y squared minus e to the, we'll say e to the x, or e to the y. Yeah, that's fine. Okay. Yeah, that's fine. So then compute the gradient of f at say 3, 0. Okay. All right. So what is the gradient of f? As we saw, it's just the vector that has the x partial in the x slot and the y partial in the y slot. Okay, and so I need to compute partials in order to compute the gradient. So what is the x partial of f of xy? The x partial of the first term is 3x squared y squared. The x partial of the minus e to the y term is 0, right? Okay, so this is what I have here. The y partial of f, going term by term, the y partial of the first term is 2x cubed y minus e to the y, right? The y partial of e to the y is just e to the y. Okay. So then now I compute and evaluate both of these things at 3, 0. So the x partial at 3, 0 is 3 times 3 squared times 0 squared. Well, that's 0. And the y partial at 3, 0 is 2 times 3 cubed times 0 minus e to the 0, so it's minus 1. Okay. So the gradient of f at 3, 0 is the vector 0, minus 1. Right? Or if you like, 0i minus 1j. Okay. All right. So that's the gradient vector. Okay. So what is the gradient vector computing? Now, it can be a little bit confusing. Let's bring this back for a second. It can be a little bit confusing because you look at this gradient vector, it's defined in terms of the partial derivatives. You look at the picture that you have here, and because you associate derivatives with objects that are tangent, right, you might be tempted to say that this gradient vector is like tangent to the graph of this thing at a point. But be careful with that because that's not actually how it's going. As we'll see, it is a related thing, but it's not the tangent vector. Okay, it's not the tangent vector, but it allows you to describe vectors that are tangent. So that should kind of hint to what it actually is. Okay. So as we will see, the gradient vector actually allows us to define a normal vector in a way that determines the tangent object. So we'll see that by the end of class. Okay, but it's not a tangent vector to this thing. So don't think that. It's not, that's not exactly what's going on here, even if that's kind of the thing you want to think about. The better way to think about it is, yeah, the gradient vector itself is not, don't really think about it as a tangent vector, but it allows you to find tangent vectors. Okay. All right. So, why this talk about the gradient? Because now I can define the directional derivative. And I can do that in terms of the gradient. Okay. So this is a definition of directional derivative. Okay. So, the directional derivative of f at x naught, y naught in the direction specified by a unit vector u. So this is a long definition. So directional derivative of f at x naught, y naught in the direction specified by a unit vector u. Now, technically I have to make some assumptions here. I have to say that, well, we only talk about this when f is a function that has both its first order partials, and these are nice. But assuming that that's the case, the directional derivative of f at x naught, y naught in the direction specified by unit vector u is written as d sub u of f at x naught, y naught. How do I compute this? I compute this by finding the gradient of f at the point in question and dotting it with the vector u. Okay. So I compute the gradient of that function at that point in question, and I dot it with the unit vector in question, and this gives me the directional derivative of f at that point in the direction specified by that unit vector. And as we saw last time, this computes, or as I saw in the lead up here, this was the thing that the directional derivative is supposed to be computing. This computes the instantaneous rate of change of f at x naught, y naught in the direction specified by u. Okay, where u has to be a unit vector. So this is going to be a recurring theme on any future assignments, exams, or whatever involving these quantities. So the way that this works is you'll be given a vector. Maybe it's a unit vector, maybe not. If it's not, then you have to turn it into one, right? Which you have no problem doing. Okay, so let's do a quick example. Let f of xy be 6 minus 3x squared minus y squared. And let's find I'll phrase it like this. So find the directional derivative of f at 1, 2 in the direction, maybe I should say, in the direction of the vector v, which is I plus j. Okay. Okay. So how do I do this? Well, I'm not always going to be so nice to give you the letter, for the vector being something other than u. Right? Sometimes I will call the vector u, and it won't be a unit vector. All right. In this case, I called it v, and it's not a unit vector. But I want to compute the directional derivative, of course, in the same direction indicated by v, even though it's not a unit vector. So I have to make it a unit vector. Right? So I find a unit vector in the same direction of v. And of course, the way that I can do that is just taking the vector that I've been given and dividing by its length. Right? Okay, so this is a trick you can always do so long as the vector you're given is not the zero vector, and we're not going to be that interested in computing directional derivative in the direction of the zero vector. So this is something we're basically always going to be able to do. So our vector is v, which is just 1, 1. The length of that, of course, is square root of 2. So dividing by the length, this is 1 over root 2 I plus 1 over root 2 j. Right? So that is unit vector in the direction of v. Okay. All right. Now, in order to compute this directional derivative, I need to compute the gradient, which means I have to compute partials, right? So remember that thing I said last time about every single problem from here on out for chapter 13 involving computing partial derivatives. So what is the x partial of f? So the x partial of 6 is 0. The x partial of minus 3x squared is minus 6x. The x partial of minus y squared is 0. What's the y partial of f? Well, the y partial of 6 is 0. The y partial of minus 3x squared is 0. The y partial of minus y squared is minus 2y. Okay. And now I was asked to compute this directional derivative with 0.12, so now I plug 1, 2 in here. Of course, each of these actually only depends on x and y. But what is the x partial at 1, 2? Well, it's minus 6 times 1, so it's just minus 6. What is the y partial at 1, 2? It's minus 2 times 2, so it's minus 4. Okay. And so what is d sub u of f at 1, 2? This is the gradient of f at 1, 2 dotted with u. Right. This is the gradient of f at 1, 2. The first component is minus 6, second component is minus 4. Here's u. So this is minus 6 over root 2, right, plus minus 4 over root 2. And so this is minus 10 over root 2. Notice, right, something I didn't mention when I wrote this thing out, that my directional derivative is defined as a dot product, which means it's what kind of object? Well, it's a scalar, right? So when I compute the directional derivative of a function at a point in some direction, that's always some scalar. It's always some real number. Okay, that's important because otherwise it's a little confusing, right? If this is really going to mimic what we know from Calc 1 and Calc 2, when I computed the derivative at a point in Calc 1 or Calc 2, I got a number, right? That number was the slope of the line tangent, which, of course, represented this instantaneous rate of change. So our instantaneous rate of change was a number, it was a real number. So this is mimicking that, right? Our directional derivative is given as a real number. So there it is, right? Now, you could say, like, what exactly does this mean, right? Well, this is telling me, relative to some units, what my rate of change is in the direction specified by u for this function. Okay, and that's as good as I need to know. Okay. All right, so I didn't see any other questions about that in the chat, so that's cool. All right, let's quickly compute Or maybe I should mention some important facts first. So naturally, right, the second that I write out this fact, so the directional derivative of f at a point x naught y naught in terms of u. So I defined this to be the case. This is the gradient of f at x naught y naught dotted with u. Okay, so the second we start computing these directional derivatives, as you saw in the last example, maybe you have some natural questions like, what does this mean? And can I tell somehow what the maximum possible directional derivative is at some point? Okay, that is, can I find the direction in which this rate of change is maximal? Okay, and in that direction, right, what is this rate of change? So maybe I'll write that out. So question, maybe two questions, right? What is the direction of maximal change? So what is the direction of maximal change, okay, for f at x naught y naught, i.e. among all unit vectors, right? So the idea here is look at this thing, look at this expression, and ask yourself, okay, now let u be just any unit vector, so it's varying over all the unit vectors. The question is there a way to determine, right, just from looking at this, what is the direction of maximal increase, maximal change for this function at that point among all possible unit vectors u? It turns out there is, but there's a follow-up question here, which is, in this direction, what is this rate of change? I.e., what is the value of the directional derivative in that direction? Okay. So it turns out that there's actually nice answers to both of these. Okay, so there's nice answers to both of these. So answer. For one, what is the direction of maximal change for f at x naught y naught? The gradient of f at x naught y naught specifies the direction of maximal increase or maximal change. Okay, so this is important enough to put stars here, because this is also a nice conceptual characterization of what the gradient does. Okay, so one way of thinking about what the gradient vector does for a function is it tells you in what direction the function is increasing most rapidly, or is changing most rapidly. Okay. Now, it's a little, I say maximal increase, really I should say maximal change. What I said is not really false, as we'll see. It's actually 100% true, but it can be a little bit confusing because it also, basically, this gradient is going to point out the direction of maximal increase and the direction of maximal decrease. It's going to point out the direction of maximal change, period. Okay, so that's why it's probably better to put change here. But what I had written was perfectly fine. So this specifies the direction of maximal change. That means that the unit vector in the direction of the gradient is going to, if I compute the directional derivative of that, we can actually see what this value is. Well, let's do that, right? What is the unit vector in the direction of the gradient? Well, u defined to be the gradient of f at x naught, y naught, divided by the length of the gradient of f at x naught, y naught. This is a unit vector in the direction of the gradient, right? Okay, which means I can compute the directional derivative in this direction. So if I'm claiming this, if I'm taking this fact as true, that the gradient is going to specify my direction of maximal change, I want to compute the directional derivative in the direction of u, right? F x naught, y naught. But then the directional derivative is from here. It's the gradient dotted with whatever this u is, right? So it's the gradient of f at x naught, y naught, dotted with, here u is this thing that I've defined. It's the gradient of f at x naught, y naught over the length of the gradient of f at x naught, y naught. This is just a scalar, whatever it is. It's a scalar valued thing. When I dot gradient dotted with gradient, what do I get? When I take any vector and I dot it with itself, what is that? That's really the length of the vector squared. And so really this is the length of the gradient of f at x naught, y naught squared divided by the length of the gradient of f at x naught, y naught. So the 2 goes away, and what I'm left with, of course, is the length of the gradient of f. What was I computing here, though? I was computing the value of the directional derivative in this direction of maximal change. So what is this quantity? What is the length of the gradient telling us? It's telling us the value of the directional derivative in that direction of maximal change. So it's telling us the maximal change in that direction. Or sorry, for f at that point. So i.e. the maximal rate of change for f at x naught, y naught is the length of the gradient of f at x naught, y naught. So, nice way of thinking about this is the gradient vector specifies the vector, the direction in which the function is increasing most rapidly, and that rate of increase is given by the length of the gradient. Okay, and so the gradient is very closely associated with the rate of change of this function, right? And so it is acting as this object that allows us to answer all these questions about the rate of change of the function. And so, as I said, a way of thinking about this is if you think about the directional derivative now, taking values over all unit vectors based at some point, then the value, right, the unit vector you can plug in that actually specifies this direction where the maximal rate of change happens it's determined by the gradient. So if you want the unit vector, you would take the gradient and divide it by its length. And that gives you the unit vector that maximizes this rate of change. Okay, so that's why the gradient is important. This same fact is true for functions of 3 variables as well. Okay, so literally replace everything, right, with the three variable version. So the directional derivative in the direction of a vector u, now u has three components, but that's fine, is the gradient of f. So I should, to indicate I'm doing it at a specific point, so I would have the gradient of f dotted with u, right, where u is some unit vector in 3 space instead. Okay, and the same facts are going to be true. So the direction of maximal increase for a function of 3 variables is the direction of the gradient, and that rate of maximal increase is the length of the gradient. Okay, so the exact same facts that I just pulled off the screen, this is true if you just replace every function of 2 variables with a function of 3 variables and do the obvious swap. Okay. So everything is true for functions of 3 variables as well. Now, you might complain here and say, well, why are we doing this for functions of 3 variables? Because, you know, I can't even graph these things because their graph would require 4 spatial dimensions and I can't even visualize what's going on there. You'll see soon why we have to talk about this. Okay. So now for some conceptual things that illustrate what is going on with the gradient. And this is something that is not at all maybe immediately clear. So if I have a function of 2 variables, right? I have a function of 2 variables. And I ask you, what's the graph of this thing look like, right? Well, if we're lucky, it's nice, and it looks like this. Okay, so the graph of a function of 2 variables looks like a surface if f is nice. Okay, so it looks something like that. All right, fine. But what does a plot indicating the following equation look like? F of xy is equal to constant. Or from now on, I'll just write f of xy is equal to c. What does that look like? All right. So, for instance, if f of xy is x squared plus y squared, what does the graph of that look like? We already saw earlier last week when we were sketching the graphs of these things, we saw this is a circular paraboloid. Oh, by the way, I keep forgetting to put a nice list of some of these shapes. I'll do that before class on Wednesday. So the graph of this thing looks like this. Right? That's what the graph of this f looks like. Okay. But what if I take this f and set it equal to a constant? What does the graph of this look like? Well, even though the graph of f, of course, is a 3-dimensional thing, the plot indicating the relationship x squared plus y squared is equal to c, where does that lie? That doesn't lie in space, that lies in the xy plane. So its graph is very much 2-dimensional. What is this graph? It is a circle of radius root c, right, centered at the origin in the xy plane. That's what this is. So the graph of f is some function, right? It requires 3 dimensions to plot this, some surface, okay? But the plot indicating f of xy is equal to constant is a curve in the plane. It's not a function, right? It's definitely not a function, fails the vertical line test, so it's not the graph of a function. It is a plot of a curve in the plane. You should know this, though, because what is this curve? This curve is just one of these level curves, right? So it's just one of these z equals c curves being indicated here, right? And of course, if we chose different values of c, we would get different ones of these level curves. Maybe we could even plot them on the same xy plot, and that would be us projecting down to the xy plane here. Okay. All right, and so this defines a level curve. So f is a surface, but f of xy equals c defines a level curve, a 1-dimensional thing. So surface is 2 dimensions, right? So the graph of f itself is two-dimensional, but it sits in three-dimensional space. F of xy equals c is a level curve. It's one-dimensional, but it sits in two-dimensional space. Now, why am I beating you over the head with this? Okay, so then how can I visualize what the gradient of f at a point x naught, y naught is doing? Okay. Well, it turns out that if I have a function f that defines a level curve f of xy equals c in the plane, the gradient of f determines the tangent object to this level curve at a point. What do I mean by that? It determines the tangent object. Well, to a curve at a point, so maybe if I pick a point right here, you're not too worried. You're like, what's the tangent object here? Well, what I mean by that is it's just the tangent line at that point. And I claim that is specified somehow by the gradient. This isn't a function though, right? And if I pick really tricky points here, what should the tangent object be? Well, it should be this thing, right? But that's a vertical line, and you know that that's tricky to deal with if you're doing this in the normal way in Calc 1 or Calc 2 land. But actually, it's not too bad at all. What do I mean when I say this determines that object? To determine a tangent line, a simple way to do that is to pick a vector in the plane that is normal to it. Oh. What is that vector? If this is x naught, y naught, what is this vector? It's the gradient. What is this vector that determines this vertical line? See, this is a vertical line. That's a nasty object, but the vector that determines it is a very simple vector. And it's the gradient of f at x naught, y naught. So what am I saying? Well, what I'm saying is the following. So written out in words, that's the nice picture showing you what's going on. But here's the following. So theorem. Okay, so let C be the level curve f of xy is equal to constant. Okay, let x naught, y naught be a point on C. Okay. If C is smooth, and we'll assume that, so this is good enough to get you what you want, but f is differentiable, which means it has its first order partials at x naught, y naught. We don't have to worry about any of that. So if C is smooth, and if the gradient of f at x naught, y naught is not the zero vector, okay, then the gradient of f at x naught, y naught is normal to C at x naught, y naught. Okay, so that's just writing out what I showed in the picture. Why am I mentioning this? You might see where I'm going with this. Okay. Well, here's where I'm going with this. What if we have a function, f of xyz, right? And I want to talk about the graph of this, right? What does the graph of this look like? I don't know. I would have to engage in some weird arguments about looking at cross sections, and of course the cross sections here would be three-dimensional, which would already be a little weird. And if you've ever heard of a book called Flatland, it was written in the 1800s. It's actually a really nice book that kind of helps visualize what it would mean to have a fourth spatial dimension, right? One of the observations is if there was a fourth spatial dimension that a four-dimensional being had access to, then you could perform surgery on a three-dimensional being by pulling organs out of the fourth dimension, and it wouldn't break their skin, right? Because their skin is bounding a three-dimensional, region that is, in those restricted to those 3 dimensions. You could pull organs, out in the 4th dimension. It wouldn't break their skin because you're not accessing those dimensions that the skin are bounding. So anyway, I'm not even going to try to engage in any drawing here. This is a 4D thing. Right? But before there, let's go back here. But here we had a graph, or we had the graph of a function of 2 variables. That was a 3D thing. Graph of a function of 3 variables is a 4D thing. But if I set a function of 2 variables equal to a constant, that was a 2D, it was a 1-dimensional object, but it required a 2-dimensional graph here, right? And so what if I, for a nice function f, set f of x, y, z equal to a constant? What do I get there? Well, I get something like this. This is called a level surface of f of x, y, z. So the analogy is exactly the same. Quick example, right? If I pick f of x, y, z to be x squared plus y squared plus z squared, well, what's the graph of that? I don't know. It's hard to draw, right? I can't draw it on 2-dimensional paper meant to be representing a 3-dimensional object of a 4-dimensional graph. That's not going to fly. But what is f of x, y, z? What is this thing if I let this be equal to a constant? What is this? It's a sphere, right? This is a sphere of radius square root of c. Okay. So I took a function of 3 variables, set it equal to a constant. What I get is a surface. Okay. All right. In general, it's some surface that's not the graph of a function. That doesn't have to be the case. Okay. In fact, as it turns out, every function of 2 variables the graph of it can be realized as a level surface. Okay. So here is the absolutely key fact here. Every graph of f of xy, that is a function of 2 variables, can be realized. Of course, if f is nice in the sense that it's continuous, right? The graph of the thing is a surface in itself, can be realized as a level surface for some function of 3 variables that we'll call g of x, y, z. This is a very important fact. So every f of x, y can actually be thought of as a level surface for a function of 3 variables. This is also why we can't escape having to do some of these computations involving functions of 3 variables, because they're hiding in plain sight. Okay, how do I do this though? It's actually really easy. If I graph a function f of xy, what is that? That's me saying that z is equal to f of xy, right? Z is equal to f of xy. Well, if z is equal to f of xy, then f of xy minus z is equal to 0. Okay. Now you see where this is going. Define g of xyz to just be f of xy minus z. Then the graph z equals f of xy is the same as the level surface g of xyz is equal to 0. And so every graph of a function of two variables can be realized as a level surface of a function of three variables. Just like if I wanted every curve that I had encountered in Calc 1 or Calc 2 that's a function of a single variable could be thought of as a particular level curve for some function of two variables. Okay. This is going to allow us to define the tangent object to such a level surface, just like we define the tangent object to a curve in the plane using the gradient. Okay, now our tangent object here to a surface is no longer going to be a line, it's going to be a tangent plane. Okay, and so that's what we'll do next time. Okay, at the beginning of class next time we'll define the tangent plane to the graph of a function, f of xy. So, I think that's all for today. So I will see you all on Wednesday where we'll start on that.